second week of the workshop on graphs and randomness. For the people who weren't here last week, so the idea is going to be that we're going to have just a few talks from fantastic people, and there'll be a mini course by Remco. But most of the time, you're supposed to talk to each other, work on problems together. So after Oliver's talk, there'll be a problem session. So please, whilst paying attention to Oliver's talk, think, if you haven't thought of a problem already, then try and think of a problem to suggest. The idea is the problem should be well, interesting, but sort of not so difficult that there's no hope of solving it in the next week. And it's a problem, preferably a problem that you might be interested in talking to other people here about. Anyway, so our first speaker is Oliver Riordan of the University of Oxford. Oliver is one of the world experts in random graphs and percolation, also author of a wonderful book with Baylor on percolation. So it's a tremendous pleasure to have him telling us about cliques and random graphs.
Yes, random cliques and random graphs.
Random cliques.
Okay, thank you. It's very nice to be here. I've been in Rio a few times before, but never quite so long. It's very nice to be here in such a pleasant, relaxed environment where everything is very relaxed, so you can have lots of energy left for doing mathematics rather than other things. If you were here last week, the topic was probabilistic combinatorics, and not all the talks were exactly probabilistic combinatorics. This week's topic is something else, I can't remember what, but my talk, actually I do remember, my talk is definitely probabilistic combinatorics. It's sort of a classical kind in a way. Well, you can pretend it's about models of random somethings. Okay, I'm going to give a Blackboard talk because I want to describe a proof, because I have a proof that can be described in a talk, I think. Not completely all details, there are some calculations, but maybe, depending how the time goes, essentially the complete proof. I assume he's going to do it. So when sitting in the audience in a previous Blackboard talk, a very clever thing was that the cameraman was showing the current board enlarged there. So as the audience, that seems to only have an upside. But when I stand here now, I realize there's a disadvantage, which is if I write on this board and you're sitting near the back and you can't read it, you think, well, it's not very big, I'm sitting a long way away, maybe it's my fault, I should have sat in the front. When you see it enlarged, you'll realize if you can't read it, it's not your fault, it's my fault. Sorry. Okay. The structure of the talk will be, I'll describe the problem, then the result, then the result, then maybe some motivation, and then the proof. So the problem is sort of how random are the, let's say, triangles, or we might be interested in copies of KRs in GNP. Okay, that's very vague, so let's start to make it more precise. So GNP, I mean, I think if you're here, you know what it is, but let me say it very briefly. That's the classical binomial random graph model, or Erdős, sort of essentially introduced by Erdős and Rényi model, where we have a fixed set of n vertices, and each possible edge is just there with probability p independently of the others. Okay, so you take this random graph, then you can look at various subgraphs of it. So for example, you can say, where are the triangles? Okay, here's one. That gives a sort of different random object. So you can look at where are all the triangles. Well, each set of 3 vertices either forms a triangle or doesn't. So you can think of that like a random hypergraph. Okay, so I mean, what's in this case R uniform? At the moment R is 3. Hypergraph. It's just a finite set of vertices, which in this case, as usual, will be 1 up to n, and then a set of edges, which is just a set of R element subsets of the vertices. Okay, so for R is 2, that's exactly a graph. So if we take GNP, then we can form the triangle of a KR hypergraph, where we just say an R element subset is present as an edge in the hypergraph if that triangle, or KR, is present in GNP. Okay, so we get the sort of the R uniform hypergraph derived from GNP by looking for the KRs. Okay, that's random. It's a hypergraph. But is it the first random hypergraph you would think of? Okay, which is what? It's just the hypergraph equivalent of GNP. So let me call that, say, HR. I want to write a different thing because the p's are going to be different when we start connecting them. So HRN pi, that's the binomial random hypergraph, R uniform hypergraph. What does that mean? Each possible edge, so R element set, is present with probability pi independently of the others. Okay? Right. Random hypergraph. Are they the same? Are they similar? Okay, they're definitely not the same. And the reason they're not, so, I mean, to be the same, we would have to take pi to be p cubed, because the probability a particular triangle is present in GNP. Now, I'm thinking of r equals 3 much of the time, just for explaining. Sort of forget to say that. So a particular triangle is present with probability p cubed. Okay, but if you look at sort of two particular triangles, so the probability, the triangle with vertices 1, 7, 11, and the triangle with vertices 7, 11, and 8 is present in GNP. What's that? It's just p to the 5th, which is not the same as pi squared. So you get in this random hypergraph, the edges are not independent where they overlap. So in the hypergraph, the probability that these two edges are present, they should all be independent, it should be pi squared. Okay, so they're not the same, but can you compare them? What is a nice way to compare there are two random objects with the same space, two probability distributions on the same thing. A nice way to compare them would be some kind of coupling that puts one inside the other. Okay, so with apologies to the experts, let me very briefly say what that actually means for those who are not familiar. So what does it mean to couple two, I mean, sometimes we loosely say two random variables. We shouldn't. We should say two distributions. So sort of random variables are really two distributions. It means just to construct random variables with these distributions on the same space. I think I owe an apology for writing too well so far. Having said my handwriting is terrible, I think this is pretty good, but it'll probably get worse. Right? Maybe you disagree. Okay, there's some shakes of the head from the audience. This is my good handwriting. But if something is not clear, please ask. And especially, I believe I can speak clearly with a microphone. So do ask if anything is not clear, please. Right. So which doesn't say anything, but usually with some additional property. So to give a sort of a silly example, if you'd like to take a look at the binomial distribution 5.5 and the binomial distribution 6.5, so one thing you can do is just toss 5 coins here, 6 coins here, count the heads. Then that random variable will have this distribution. This random variable will have this distribution, and there's no connection between them. Okay? But what you could also do is just toss 6 coins and say, sort of, x will be the number of heads in the first 5, and y will be the number of heads in all 6. Okay? So you've built, on one probability space, given by the 6 coins, you've built these two random variables. They have exactly these distributions, and now there's a relationship between them. So in this case, you'll just have x is less than or equal to y because it is. Okay? So that's a sort of the simplest possible example of what some kind of coupling between distributions means. So what might we want to do here? We might want to couple sort of GNP and therefore its derived triangle hypergraph with the independent hypergraph so that maybe one is contained in the other. Okay, and not with pi exactly p cubed, because that would be impossible, but with pi similar to p cubed. Which way should the containment go? This gives you the answer. So in the random graph, just overall, there will be a lot more pairs of overlapping triangles than in the hypergraph. There'll be pairs of overlapping hyperedges. because this p to the 5 is much bigger than p to the 6. So p will be going to 0 at some rate, what we're looking at. Okay? So there's something that you just see more of in in this graph than in that, this hypergraph than that. So there's no way to fit this inside that without chopping stuff out. So let's try to fit it the other way around. Okay, can you do that? The answer is yes. So here's theorem. I should tell you who proved it in a moment. You may guess that I'm involved somewhere. Which is, you can do this in some range. So let R at least 3 be fixed. P equals P of n. Let me say is at most, so this is a certain function that is natural for a reason that I'll explain later, plus a little bit. Actually, I can go up to some constant here. So for each r, there exists a constant epsilon, so you can put plus epsilon there, but let me not bother. Then there exists another function pi, which is roughly p to the r choose 2, which is the analog of p cubed, pi twiddles p to the r choose 2, such that, such that we can couple the couple of random variables, blah, 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 so that with high probability, meaning with probability 1 minus little o1 as n goes to infinity, as usual, we have the containment whichever way around was true. So h r n pi is contained in the sort of triangle or KR hypergraph of our random graph GNP. Okay, so what does the coupling say? It says you can generate GNP and this hypergraph on the same space with the property that for every hyperedge in the random hypergraph, there is a triangle or a KR in GNP, but not vice versa. Okay? Right. Who proved it? So if you see a result like this, there's something you know instantly if you've done anything like this before, which is that RS3 is special, and it's special because it's easy. Okay? And I mean, there are two possibilities. Either it's all the same, or R3 is easy and then it gets hard. Maybe it gets hard in one step, maybe it gets hard in several steps. 4 is a bit harder, and 5 onwards needs a different argument, and so on. This is the only exception that I know of. So R4 onwards is easy. So I did that. And for R equals 3, there's an extra difficulty, and I produced a partial result. And then Annika Heckel, a postdoc in Oxford, did that. Okay? So she did the harder bit, not the easier bit, which is strange. Right. And she did it quite quickly. So I was thinking about this last summer, meaning last Northern Hemisphere summer, and then I wrote it up this summer, meaning this Southern Hemisphere summer, a couple of weeks ago. And then Annika saw that and did the missing case. Right. That was the result. What comes next? So some motivation. I personally don't think this needs motivation. For my own taste, this is just the question, how do you relate? You know, how randomly distributed are the triangles in GNP is just natural in its own right. But there is some motivation, and that relates to the F factor problem.
Can I ask you a question?
Yes.
So when you say that pi is of the order of b raised to r, which is 2, you really mean 1 plus the whole?
Yes. Okay. Which is about to become important.
Yeah, so it also means that the two graphs are close in some sense, right? So
Yes. Oh, yeah. They're very close. So even though you see a lot more overlapping pairs in one than the other, most pairs don't overlap. So or most triangles aren't in an overlapping pair. So that's still quite a small part of the graph. So in this coupling, you've found, so for every hyperedge here, you found a triangle here. But the number of hyperedges here is almost exactly the number of triangles here. So you found that almost all the triangles in GMP are sitting like these completely independent things, even though if you go to all of them, it's just not at all true that they're independent. Yeah, so it's a very, very close match in some sense, although only in a one-way sense. Maybe it's surprising that it's true, I don't know. But once you think it might be true and start trying to prove it, it's not that hard. Okay, why is it interesting? So I think for me the interest is the random graph side. Random hypergraphs are also interesting, but random graphs, I mean, that's what most of probabilistic combinatorics is studying GNP. That's what lots of us have been doing for the last few years, few decades, as appropriate. What kind of questions can you ask about GNP? So a lot of the questions, maybe most of the questions, are threshold questions. So, which is basically how large does P as a function of n need to be that the probability, and there are different types of threshold questions, but one of the most common is to look at the probability GNP contains a certain thing, that this becomes likely rather than unlikely. Okay? I mean, this is one of the main focuses from the beginning. Erdős and Rényi asked it for these specific subgraphs. You ask for K4 or something. They answered many of them in 1960. Baylor answered all the rest in 1981. But you could also ask not for fixed subgraphs, but for something that's growing with n. So, for example, you could ask for matching, so a complete matching. So to find n over 2 edges covering all the vertices, we assume without comment that n is even when asking that question. Again, I think that's known since 1966 or something by Erdős and Rényi. What about some other big spanning subgraph? So Hamilton cycles is a very well-studied example, which again, there's a relatively simple answer. But what about, say, a triangle matching, so a triangle factor? So n over 3 triangles covering all the vertices. Or in general, you can ask for a, let's say a KR factor. I don't actually know where the question goes back to because the papers I've looked at about it don't give a proper attribution. I assume this goes back to Erdős. So either Rob or Baylor probably knows. But the question, what's the threshold for a KR factor? Okay. But the Hamilton problem was quite a while in nature. So yeah. Mm-hmm. And OSHA's trace so it's not easy. It's infinitely more difficult. True. And the matching. Yeah. Mm-hmm. And then this one's infinitely more difficult again. So this question has been looked at quite a lot, and there is partial result on it by, for example, Rudzinski, 82, Alon and Juster, 93, Krivolevich in 96, Kim in 2003, and then this was solved by up to a constant factor by Johansson, Kahn, and Vu in 2008. Johansson, Kahn, and Vu in 2008 in a paper with this amazingly complicated and clever argument. What's the connection? Well, this is about the triangles in GNP. So we could relate it to a different question, which is we could use the hypergraph instead. So we could look for a factor, a matching, in the hypergraph. And what the theorem does is it lets you reduce one to the other. And it's the right way around. It reduces the harder question to the easier question. Okay? So this is related to what's known as Shamir's problem. Again, I don't know a proper attribution, which is just the sort of hypergraph version, but looking for a matching. So threshold for a matching in the random hypergraph in HR n pi. Okay, and in both of them, one way around is easy. We know when there isn't a KR factor. We know when there isn't a matching. So the problem is to show there is one. And with the theorem, if at the right density you've shown that there is a matching here, that just means a set of disjoint hyperedges covering all the vertices, then that theorem says for each of these edges you find a triangle in GNP. So it reduces one to the other. Okay, is that useful? So in this paper, this easier question is not easy either, and it was only answered at the same time by Johansson, Kahn, and Vu. up to a constant factor. So until a couple of weeks ago, the only application for this theorem that I know of was to say, in that paper, you could simplify part of the argument by only doing hypergraphs and then using this theorem to convert to triangle KR factors. Okay, but a couple of weeks ago, Jeff Kahn announced that he has proved a much sharper version of this with not just a constant factor, with 1 plus little o1, so the sort of sharp threshold result. And then this sharp threshold result plus that theorem gives you, sorry, but he's only done that for hypergraphs. He's not done that for KR factors. But maybe he could if he tried. But knowing this, he said, OK, that's good, I don't need to. So there's a sharp hypergraph matching threshold result announced by Jeff Kahn. I assume it's not written up yet. It may take some time. And that result plus this gives you a sharp threshold result for the KR factor in GNP. OK, so that's the application and motivation. I don't know why I'm looking at my notes. I don't have any notes. So, I have notes what the plan of the talk was, which was what's the question, what's the theorem, what's the motivation, and what's the proof. So I think now I have to just prove the result. Let's see how far we get. Right. So the global strategy of this proof is there's a sort of German word for the attitude that goes with it, which is Betonkopf, so concrete head. So you think of the problem is sitting there. You just put your head down and you charge at it in the most simple way possible. You don't think about what you're doing. Just go ahead. At some point, you'll sort of hit a wall. It doesn't work. But just keep going. Just go through the wall. So I want to try to do the simplest possible thing. It won't quite work. But when it doesn't work, you don't give up. You just fix it. You just make it work. And that will work. So what is the... So how do I think about this? So in each case, we've got sort of n... I think about r equals 3. We've got n cubed things. So the capital N is n choose r, roughly n cubed things in the triangle case, which may or may not happen. So we can think of, let's say, E1 up to En are all the edge sets of possible triangles, or KRs, in GNP. And let's say AI is the event that EI is present. It's contained in the edge set of, maybe from now on, G equals GNP. OK, and on the other hand, we've got an event, but I prefer to talk about an indicator function. It's just slightly more convenient also to separate the two. So we've got GNP and we've got the hypergraph. So I'm going to have II is going to be the indicator function, so just 1 or 0, of the event that the corresponding edge is present in the hypergraph. So corresponding to EI is in HR n pi. OK, what's the distribution of these? They're just independent. OK, so the random hypergraph, it's got structure because it's a hypergraph, so things are sitting on vertices, but the randomness in it has got no structure at all. There's n choose 3 things that may or may not happen. This hyperedge is in or not, this one is in or not, this one is in or not. These things are just 1 or 0, according to whether it's in or not. Each one is 1 with probability pi independently of the others. Okay, that's the randomness in the random hypergraph. So I1 up to In are supposed to be independent, and each II is 1 with probability pi. OK. So this is the easy bit. That's the hard bit. So we sort of think about this and try to compare it with that. OK. How do you... So I could write the indicator functions for these events, but I'm not going to. So what do we want? We want to build the two distributions on the same space so that, with high probability, whenever AI holds, then II is 1. OK? And so I'm going to take GNP as sort of given, so that GNP will have the right distribution. And I want to build the right distribution for these. OK. How do you build the right distribution for a sequence of independent indicator functions? Let's try to do it one by one. And what does it mean? It just means that whatever's happened so far, when you get to the next one, the probability it's 1 should be exactly pi. Okay? So we're going to build this random sequence, and what we want is the probability II equals 1, given the history, given everything we've done so far, should be pi. So, and if we construct them one by one with this property, they have the right distribution. Okay? That's not an idea. That's just what it means, what this distribution means. Okay. So how should we do that in the graph? Well, we should just look at these events one by one and see whether they hold. Okay? That's not it, but that's almost it. And that's it apart from the problem. But the problems are all soluble. So what we're going to do is we'll just test sort of our random graph GNP to see whether the event AJ, I write J for a reason, because we'll have I less than J later, holds. Okay, so we'll just go one by one through them. So for J equals 1 up to n, we'll test whether AJ holds, and let's look at the conditional probability. So pi j be the probability that AJ holds given the history. Okay, when would we be done if pi j is at least pi? Then we're happy, because we want, which way round is it? We want the ij to be 1 with probability pi, and whenever it's 1, the event aj holds. Okay, so in that case, what we could just do is then when aj holds, I mean, the probability is a bit too big, but we can reduce it. So let's just toss a sort of new coin, a new coin which has probability pi over pi j, coin being heads, and if that's heads, then set ij to be 1. Okay, so there's a mini idea here, which is that we're just asking whether the event holds or not. So we want to know as little as possible. Okay, why? Because at the beginning, if I say, what's the probability this triangle is present, it's p cubed. Okay, but after a while, I know something about the graph, and that's messing up the probabilities. So it's sometimes in a good way, or a harmless way. So if I said, I know this triangle is present, and I ask, what's the probability this triangle is present? Now it's p squared, which is bigger. That's fine. But sometimes in a bad way. So, and for the bad information, we want to know as little as possible, so it will have as little negative effect as possible. So what I don't do is ask, is this edge there? Is this edge there? Is this edge there? Because if I get an answer no here, then that kills me later for all possible triangles involving the edge. Okay? Instead, I ask the single question, are all 3 edges there? Because that's what I need to know, so I should only know what I need to know. Okay. Because knowing things is bad in this context. Right. Okay. So that's the first thing. The second thing is, what happens if not? Pi j is less than pi. Should we give up? The answer is no. It hasn't yet gone wrong. So we can't make the coupling definitely work in this case. But we can still try. So our ij should be 1 with probability pi. So let's just set it to be 1. So again, sort of with toss a new coin independent of everything so far, just set ij equal to 1 with probability pi. Okay. Yeah, it will turn out that actually that in this case pi j is 0. So when probability, when we do this, it's gone wrong. Okay. If this happens, so but only if this bit happens, then our coupling has failed. Okay. okay, that's sort of, okay, or at least it might have failed. So we don't give up if it might have gone wrong at the next stage. We only give up when it's actually gone wrong. And that's a big difference because pi is quite small, something like 1 over n squared for the triangle case. So there can be about n squared times where the conditional probability was too low, but in the hypergraph, it takes about n squared times before you actually get 1, where it happens that the hyperedge is present, even though we didn't find it in GNP. Okay? But anyway, I mean, why does this work? Just by definition, the conditional probability that ij is 1, given what's happened so far, is exactly pi in either case. So we're constructing the right distribution for the i's, so for the hypergraph. In this case, whenever there's a 1 here, aj holds, which is good. In this case, there might be a 1 here, but aj doesn't hold. That's bad. Okay, but we'll try to show that is unlikely to happen. So this case, that we set it in 1, in this case, we need to show that's unlikely, that happens at all in the process. Yes. There's one sort of mini idea, which I'm not sure it's actually relevant, which is this is not optimal because we want to know as little as possible. And here I said, let's see whether aj holds. And if it does, with this probability set ij equals 1, you can just swap the order of those. It's a minor thing. So rather, a better version of here is with probability pi over pi j, test whether aj holds. Okay, and then if yes, ij equals 1. So we toss the coin first and then do the test. So we end up doing fewer tests. That's a sort of minor tweak, but it has the advantage that any time we've seen that aj holds, we also have ij equals 1. Because here, well, yeah, here we don't even bother testing aj. Here, if we test aj and get the answer yes, we definitely set ij equals 1. Okay, so that tweak has the advantage that if we tested aj and got the answer yes, then ij equals 1. Okay.
So there's another potential gain that you're giving up there, which is you've stopped, you've kind of declared failure with probability pi, well, in fact, you just need to do probability pi minus pi j.
Yes, yes. I think it won't matter because in this case, as we'll see for kr, this actually is either 0 or at least pi. So, in fact, there isn't anything. But yeah, they're good. I mean, yeah. It's sort of Woolog one should do that if you haven't done the calculation yet to see what comes out. For exactly the same reason as one should do this. Well, no, not the same reason, but yeah. Yeah, that's giving up something, but it turns out to be giving up 0. So that's OK. Right, so what's left to do is to sort of bound pi j and to try to show the probability that at any step, pi j is less than pi, and this happens, tends to 0. OK, so what is pi j? So let's just think about the step j and fix what's happened so far. So what's the history at this point? We asked some questions and got some yes answers and some no answers. So let's say y be the set of I less than j, where we asked, does ai hold, and the answer was yes. Got yes, and let n be the set I less than j, where we asked, does a hold, and got the answer no. Okay, so these are random sets. What is pi j? It's exactly the probability that aj holds given for every I in y, ai holds, and for every I in n, ai does not hold. You might have to think for a moment, because it's random whether I'm even asking the questions, but is this true? Yes. So just think about the history, go back and say, GNP is hidden behind a curtain and I've got the answer to these questions, if I change it for another one that's consistent with the same answers, I would have got to the same state in the algorithm. And that tells you that the conditional distribution P given GNP given the history is exactly the conditional distribution of GNP given this. So it's fine. There's a sort of thing that might have gone wrong but didn't at that point. Right. OK. So part of this is easy. There are three parts to this. There's the sort of trivial part, the part that doesn't matter, and the part that does matter. So this is the trivial part. So when you ask a question and get the answer yes, you've just said this triangle is present. That just says these three edges are present. Okay? And this other triangle is present, and this triangle is present, and so on. Okay. GNP, what does that tell you about the remaining edges? Exactly nothing. Okay? So these yes answers, they just sort of freeze some of the edges as being definitely there, and then everything else is there or not independently with probability P. Okay? So let's write, let's say, I think I had F, but that's bad if you generalize from KR to other graphs to F factors. Let's say R for the set of revealed edges. So that R, which is a random set, of course, will be the union of I and Y, EI. So these are the edge sets of the triangles that we revealed to be present. Okay? So the revealed edges. And let's think about a sort of different random graph. So let G prime be like the random graph where the edges in R are sort of definitely present, and each other edge outside R is present with probability P independently. Okay? And in the edge sets we're looking for, the ones in R are sort of definitely there, so we should take them out. So let sort of EI dash be EI, the part of EI outside R, and let AI dash be the event that EI dash is contained in the edge set of our modified random graph. So the probability we want to calculate is exactly the probability AJ dash given the intersection I and N AI dash. We haven't really done anything. We've said some edges we know are definitely there. Let's stop thinking about those. In terms of the remaining edges, what we know is that for every no answer, a certain set of edges is not present. I mean, for example, if these were the edges that are definitely there, and at some point we got the no answer for this triangle, then we know that it's not the case that these two edges are present in the still random part of the graph. Okay? I mean, yeah, we've just translated the question. It's the same thing. Okay.
So should we do AI dash complement?
Yes. Which is bad notation because, let me call them twiddles so that I can complement them without getting so messy. Thank you. Anything else wrong?
Twiddles like bars, I complement twice.
What?
I'm just mixing.
Which is better, twiddles or dash?
You triple it, that's fine.
Okay. So, how do we bound something like this? So, if you've done a course on probabilistic combinatorics at the appropriate level, you've seen something like this in the middle of a proof. So, without the twiddles. So, in the proof of Yangsun's inequality, this is exactly what you need to estimate. How many people have seen this? Okay, some of you I know have seen it. Lots. Okay, good. But not everyone. Did Rob?
I teach it, yeah. All the students have
Okay. So let's try to estimate it in the same way. This is so. And here comes a difference between. So there's some dependence here which sort of shouldn't matter, but you can't ignore, and there's some which should matter. So in the modified random graph, we're asking, say, are these three edges present? And we've got no answers for various other sets of three edges. So It's not the case that these 3 edges are, or maybe 3 or maybe fewer. It's not the case that these edges are present. It's not the case that these edges are present, and so on. Okay? In the picture, it should matter whether they overlap with the edges we're looking for. So we feel we ought to be able to ignore all the information about the other edges. Okay, it's not that simple, because saying these are not present and this is not present, you know, this bit influences this, influences that, and so on. So you can't just ignore it, but we should think about them separately. Okay, so we do that. So we split the set n into 2 bits. So n0 for no dependence, at least morally, is the set of I in n such that ei twiddles intersect ej twiddles is the empty set, and n1 is, so this is not the empty set. And let's write sort of d0 or 1 to be the intersection over I in n0 or 1, ai twiddles complement. Okay? So what we're interested in, ij, is the probability aj twiddles given d0 intersect d1. We'd rather be conditioning on just d0. So let's do that. So this is the probability ai twiddles intersect d0 intersect d1 over probability d0 intersect d1, which is at least, if I've got it the right way around, which I have, the probability the same on top, just divide by the probability of d0. So this is the Boparna-Spencer simplified proof of Yancey's inequality so far. Okay, which is probability of a, j, so this is j. Aj twiddles intersect d1 given d0. Okay, so I've lectured this a few times, and the next step in the Boparna-Spencer version is to write this as 2 things, that conditional probability which we know, and then the probability of d1 given that, and then to do something funny that you can say, you end up conditioning on this, but it's another one of these simple events that just freezes some edges. So it sort of doesn't make any difference, and then you apply Harris's lemma. There's a better way to do this, which I told you this before, Rob. You raised your eyebrows. I told you a couple of weeks ago. So when I lectured it, Lutz Wonka was in the audience, and he asked me afterwards, why don't you write this step like this? Because then you don't need to explain to the students what a principal upset is. This is a sort of slight diversion. But Yancey's inequality, the statement is, if you have some principal upsets, then something. So how can you prove it without referring to what a principal upset is? And the answer is that the proof actually proves a version where the upsets don't have to be principal. So this is something that Lutz and I wrote down. Okay, it's a totally trivial thing. So instead of doing that, why not just do this? So it's the probability of aj twiddles given d0 minus the probability aj twiddles intersect d1 complement given d0. Okay? That's just true. And the point is, the first thing we know, that the conditioning doesn't matter, because now this is telling us something about sets of edges that are all disjoint from this, so it's totally determined by things outside these edges, so it's independent of whether these edges are present. So here we get probability aj twiddles minus this thing, and, let me write the line. If I could think while standing in front of a board, I would write fewer lines, but I can't, so I'll write out all the lines. And here, this is a down set. This is a down set. So in terms of the random graph G dash, so if you know Harris's lemma, that just tells us that these are positively correlated. So this will be at least this probability. Upset and a down set. So at least would have been good, but at most is even better, because then the inequality is the right way. So this is an upset, that's a downset, so they're negatively correlated. So this is less than or equal to that. So with a minus, we get at least probability aj twiddles minus this probability. Okay, this bit is all familiar from the Yangsun proof. Yeah, and now, again, we use the union bound. This is the complement of the intersection of the complements of things, so that's the union, and we use the union bound, and we get it's at least this probability minus the sum over I in N1 probability AJ twiddles intersect AI twiddles. Okay? But these are all very simple events, so we know what the probability is. This is P to the number of edges we're looking for, EI twiddles, minus EJ twiddles, minus the sum I in N1, P to the EI twiddles union EJ twiddles. Okay, and let's just take out a factor, so we can write it as P to the size of EJ twiddles, 1 minus Q, where Q is the sum I in N1, P to the size of, so I have all the edges that are in there but not there. And what are these? These were from the original sets but take away R. So it's all the edges that are in this but not in EJ or in R. Okay, I've done a step. I've done that EI twiddles union EJ twiddles is the same as to take away EJ twiddles is exactly the same as I take away I union EJ. And if that's wrong, then something similar is correct. Okay, whatever is written down in the paper is correct. So it's the sum P to the EI take away R union EJ. Right, so what would we like? We would like that most of the time Q is small, because this, I mean, that's at least P to the R choose 2. I mean, the worst case is if this is the whole of EJ at 1 minus Q. So if Q is little o1, if Q were always little o1, we'd be done. What we want to show is that the global event that there exists any J for which we do put the edge into the random hypergraph and Q is not small, that should be unlikely. Our coupling only goes wrong. It doesn't go wrong if just if Q is big. It goes wrong if Q is big and we include the triangle corresponding to EJ. Okay? That and is crucial because it means that we can think of this R union EJ, we can think of all of these as being present. As present in the hypergraph. I mean, that's a slightly vague statement. What I mean is, sorry?
This color is only good if you want to keep it a secret.
You can see it on the screen.
You can see it up there, apparently.
Whenever you can't see one on the screen.
Okay, so we can think of so the R edges. They came from triangles that we answered the question and got the answer yes. And assuming our coupling hasn't gone wrong yet, every such triangle is an edge in the hypergraph. The EJ one, that's the one we're currently asking. But things only go wrong if we get a yes answer when pi j was small. So in the bad event, the thing that we have to rule out, all of these edges will be present in triangles whose corresponding hyperedges are in the hypergraph. Okay? But E1 is not. Okay, so there are two different contributions to this Q. Well, roughly what is Q? So R union Rj. So my P, remember, was at most. Let me write it for R equals 3, although it's the same for all R. So, do you want to do that or not? Maybe not. So P was at most n to the minus 2 of R plus little o1, and in the hypergraph world, that means pi is at most n to the minus R minus 1 plus little o1, and that says that the degrees in the hypergraph that we're constructing are n to the little o1, not too big. Okay, so, and we can assume that R union Ej has all degrees at most n to the little o1. Okay, now with J fixed, we're trying to bound this sum qj, what different contributions can there be? So maybe I'll stop writing details, but still try explaining things. So we have to think about which I can contribute. Okay? So firstly, they have to overlap with EJ, because that's the definition here. So, I mean, how many EI contribute how much? I contribute how much? So there's the edge set EJ somewhere, and there's the sort of revealed graph, which is not necessarily connected. And then we are looking for an EI that sort of overlaps with, when it overlaps with this quite a lot, that's sort of bad. So something like this is bad. Okay? Now, roughly speaking, if we use sort of k components, okay, now I'm getting a bit vague. If you sit down and try to write this, it's not very hard at all. So I mean, this whole graph is connected, but I'm within the KR that I'm looking for, I've used disconnected bits. So suppose I use k components here, then how many, and what I want to bound is the number of edges outside this revealed graph. So suppose, for K4, if I use 2 components, there are 2 different ways of doing it. There'll always be at least 3 edges outside. If I have used 3 here and 1 separate, I need the 3 edges to join them. If I use 2 here, 2 separate, I need the 4 edges to join them. Okay, and you can write that down in general, and this is always the worst case, that you take a bunch of edges within one bit and other separate vertices. Okay, and it's a simple calculation that in this case, that's one bit. What's the number of ways of choosing the red picture to do this? So we start somewhere. We start at a vertex within EJ, for which there's a constant number of choices. Each time we follow a white edge, there's n to the little o1 choices. If we jump somewhere else, there's maybe the factor n choices. So there's some calculation that you can just write down that the number of possibilities will be n to the k minus 1 plus little o1, and then the contribution will be p to the something that you write down by thinking about the worst case, and it's just a fact that this comes out to be little o1. Except in one case, which is except if we have one component, when this bit is just 1. If we have any factors of p, that's fine. So the only thing that can go wrong, this is a very, very simple calculation. It's because KR is balanced in some sense. The only thing that can go wrong is that the red thing is entirely within the right graph. Okay? Turns out. Yeah. And then how can that happen? So we find, we find Q actually is little o1 unless, so Q which depended on J, little o1 unless there exists an I in N1 such that EI is totally contained in EJ union R, which remember is in our final hypergraph. So what does it mean? This was a no, this was not, this, we got the answer no when testing this, and because our coupling worked so far, that means that hyperedge is not present, but all the edges in it are present. So what it's saying is, we have some K4, for example, and we have a random hypergraph, the final one. This hyperedge is not present, but every edge of it is contained in a hyperedge that is present. Okay, that's certainly possible. So for example, we might have this hyperedge with 4 vertices, this one covering these 2, this one covering these 2 or something. It's possible, but it's not very likely. Okay, you have to check this, but the calculation is actually very simple. So for R at least 4, if this happens, so if the hypergraph H is such that there exists a KR, which is not an edge, not a hyperedge, but all of whose edges are covered, but all graph edges are included, are covered, then H contains something unlikely. So it looks like I'm hiding something complicated, but actually I'm hiding something simple, but it's near enough the end of the talk that I should hide even simple things. What do I mean? This hypergraph, the degrees are not terribly big. Okay? So when you explore out from a vertex, there are lots of hyperedges involving a particular vertex, but they tend to be disjoint from each other. If you ask for a hyperedge containing 2 particular vertices, the number of those would be n to the little o1 minus 1, which is 1 over n. It's unlikely. Okay? So you're unlikely to find cycles. But not that unlikely, because we have about n hyperedges to start from, more than n. So locally, a configuration like this you will find, but anything worse you won't find. So anything that's any small hypergraph that's not a tree or a cycle, unicyclic, you won't find. Any complex configuration. Small one. Globally, the whole thing is complex because the degree is much, much bigger than 1. But for any fixed size complex configuration, it with high probability won't be there. And it's just a fact that for R at least 4, you can't make a sort of spurious KR without having a complex configuration. Okay. And it's a fact that for R equals 3, you can. So that's why R equals 3 is nasty, because you can just take this triangle, this triangle, this triangle. The white things are a unicyclic configuration, which messes the proof up, so it doesn't work. Except if you're Annika Heckel, and then you say, let's deal with these things are a problem. So it's the same meta strategy, that you try the argument, something goes wrong, then you fix it. This goes wrong with this argument, so why not fix it? And her fix is to say, we understand the distribution of these in GNP and in the hypergraph, so let's examine those at the beginning of the argument. So let's test all of those, whether they're present or not. We know that bit can be matched up, because there are not so many of them, they're disjoint. And then you have to run the rest of the argument and make sure it still works when you've done this first step first, and it does. It's not obvious it works. If it were obvious it worked, I would have included it myself, but I didn't. So I didn't see whether it worked or not, but it does work. Yeah, I seem to have got to the end of the proof, so I think I'll stop.